On December 19th, 2025, something arrives. Not a threat, not a greeting, something worse, a correction. We've spent a century assuming the scariest message from space would be a declaration of war. But here's what keeps astronomers awake at night. War means there's an enemy you can see, understand, maybe even negotiate with. The truly terrifying messages are the ones that don't threaten you at all. They warn you about something else. Something that's been listening to our broadcast for decades, cataloguing our position, waiting. Tonight, we're ranking 3 types of cosmic messages from unsettling to existential nightmare. By the end, you'll understand why silence might be the only thing keeping us alive, and why 3i Atlas might be trying to teach us that lesson before it's too late. If you're finding yourself drawn into these cosmic questions the same way I am, go ahead and hit that like button and subscribe so you catch every development as this story continues to unfold. Leave a comment letting me know where you're watching from, what hour it is in your corner of the world, and your opinion on what would be the scariest message we will receive from 3i Atlas on December 19th. Part 1. Opening Punch. Breaking news on 3i Atlas. December 19th is not a prediction. It's a date, a waypoint on a trajectory already calculated, already locked in. On that day, the 3rd confirmed interstellar object ever detected will make its closest approach to our planet. The object's name is 3i Atlas, and it arrived from a place we can't point to on any map. It came from the space between stars, where nothing was supposed to be travelling at all. Interstellar objects are so new to our catalogue that we're still figuring out what to call them. Before 2017, we had never confirmed a single visitor from outside our solar system. Then came Oumuamua, tumbling through our neighbourhood like a cosmic tourist with no interest in stopping. Then came Tui Borisov, a comet that looked almost disappointingly normal, and now 3i Atlas, which refuses to fit neatly into either category. Ground-based telescopes have been tracking it for months. Spectral analysis shows chemical signatures consistent with cometary ice and rock. Nothing alarming there. The European Space Agency's XMM Newton Observatory detected X-ray emissions as the object began interacting with solar wind. Again, perfectly normal for a comet. When charged particles from the sun collide with gases streaming off a comet's surface, you get X-rays. It's basic plasma physics. But here's the thing about X-rays from comets. They're natural, predictable, and still deeply unsettling to anyone who doesn't spend their days analysing spectra. Because X-rays sound dangerous. They sound like something you should evacuate from. What makes 3i Atlas different isn't what it's doing. It's how long we've had to watch it do those things. Previous interstellar visitors zipped through our system so fast that by the time we got good instruments pointed at them, they were already leaving. 3i Atlas is taking its time. Its trajectory brought it into our solar system at an angle that gave us months of observation. Months to notice every flicker, every chemical signature, every deviation from what we expected. And with that much time comes something dangerous. Pattern recognition. Velocity matters here. 3i Atlas is moving faster than anything gravitationally bound to our sun should move. That's the defining characteristic of interstellar objects. They're not just passing through, they're escaping. But the speed itself raises questions. Too fast, and you start wondering what kind of event could fling something across light years of empty space. Too slow, and you start wondering if it's slowing down on purpose. No signals have been detected. Let me be clear about that. No radio transmissions, no optical pulses, no mathematical sequences beamed in our direction. The object is doing what comets do, outgassing, tumbling, reflecting sunlight in ways that vary based on its rotation and composition. If you want to call this a natural phenomenon, you have every scientific justification to do so. But absence of a signal is not the same as absence of information. Here's the question that keeps astronomers up at night, even if they won't admit it in peer-reviewed journals. If we did receive a message, what kind would be worst? Most people assume the scariest message would be a declaration of war, an ultimatum, a countdown to invasion. But that scenario, terrifying as it sounds, actually gives us something to work with. It tells us who's out there. It tells us what they want. It gives us an enemy with a face, or at least with intentions we can understand. War is something humans have been doing to each other for thousands of years. We know the shape of that fear. The truly frightening messages are the ones that don't resolve anything, the ones that leave you staring at data you can't interpret, listening to silence that might be deliberate, watching an object that obeys the laws of physics but still feels wrong. Because ambiguity is corrosive. It turns every observation into a question. It makes you second-guess your instruments, your models, your sanity. There are 3 levels to this hierarchy of terror. 3 types of transmissions that escalate in horror, not because they become more hostile, but because they become more uncertain. The first level is confusion, a message that mirrors our own broadcast back at us, statistically impossible to occur naturally but containing no new information. The second level is distress, a message that frames the visitor not as an explorer but as a refugee, fleeing something we can't see. And the third level, the one that keeps SETI researchers awake in the dark, is corrective, a message that isn't a greeting or a threat, just an instruction. Stop broadcasting. If the scariest message isn't hostile but corrective, it means someone out there knows something we don't. It means our presence has been noticed, and it means that being noticed might be the most dangerous thing we've ever done. Think about what that implies for a moment. A civilization advanced enough to cross interstellar space, sophisticated enough to locate us among billions of star systems, doesn't send greetings, doesn't request information, doesn't threaten conquest. Instead, it tells us to be quiet. That single instruction carries more terror than any weapon ever could, because it suggests the universe isn't empty at all. It's full of civilizations who've learned that survival depends on silence, and we've been shouting for a century. 3i Atlas will reach its closest point to Earth on December 19th. The countdown is not a theory, it's geometry. Observatories around the world are preparing for maximum observation windows. Amateur astronomers are training their telescopes on coordinates updated daily. Data will flood in whether we're ready for it or not. Whether the object is a comet, a messenger, or something we don't have words for yet, we're going to be watching. And maybe, just maybe, it's been watching back. The question isn't whether we'll receive a message. The question is whether we've already received one and just haven't recognized it yet. Because the scariest messages aren't the ones that announce themselves clearly. They're the ones hiding in plain sight, waiting for us to understand what we're looking at. And if we do understand, if the data suddenly clicks into place and reveals something we weren't prepared for, we'll face a choice no civilization should have to make. Do we listen to the warning, or do we keep broadcasting into the dark, hoping that whoever told us to be quiet was wrong about what's out there hunting for noise? Part 2. Signal versus noise. Why we'd even expect a message. Let's start with what astronomers actually see when they point their instruments at something like 3i Atlas. They're not listening for radio signals the way SETI does. They're watching how light behaves. They're measuring brightness over time, tracking what's called a light curve. They're splitting that light into its component colours through spectroscopy, looking for the chemical fingerprints of elements and compounds. They're checking for polarization, which tells you about the alignment of light waves and what kind of surface or atmosphere might be scattering them. And they're monitoring for non-gravitational acceleration, tiny changes in velocity that can't be explained by the sun's gravity alone. None of these measurements are designed to detect intelligence. They're designed to figure out what something is made of, how it's moving, and whether it fits into categories we already understand. This is why we wouldn't receive a radio hello. If 3i Atlas wanted to announce itself clearly, it would need to emit electromagnetic radiation in patterns that couldn't possibly be natural. It would need to violate our expectations so obviously that even the most skeptical scientist would have to admit something was off. But that's not what's happening. What's happening instead is accidental messaging. Emissions that aren't intended as communication but still carry information. Think of it this way. When you walk across a floor, you leave footprints. Those footprints weren't meant to tell a story, but someone examining them later could infer your weight, your gait, whether you were running or walking. The object doesn't need to be trying to communicate for us to receive a message. It just needs to exist in a way that creates patterns. History is full of false alarms in this domain. In 1967, astronomers detected repeating radio pulses from space that were so regular, so precise, that they briefly labelled the source LGM-1. Little Green Men 1. The pulses turned out to be from a pulsar, a spinning neutron star with magnetic fields so intense they beam radiation like a cosmic lighthouse. Natural, predictable. boring once you understand the physics. But for a moment, humanity thought we'd found them. Early city programs faced similar disappointments. Signals that looked artificial turned out to be interference from satellites, radar installations, even microwave ovens. The universe is full of things that produce patterns. Water mazes in star-forming regions emit microwave radiation at frequencies that could be mistaken for engineered signals. Quasars flicker, magnetars burst. The cosmos is noisy in ways that have nothing to do with intelligence. Pattern recognition is dangerous because it's unavoidable. Human brains are wired to find structure in chaos. We see faces in clouds, hear voices in white noise, and assign meaning to coincidences. This cognitive bias kept our ancestors alive by helping them spot predators in the underbrush, but it also makes us prone to seeing signals where none exist, and now we've automated that bias. Artificial intelligence systems flag anomalies faster than humans can contextualize them. Machine learning models trained to find outliers will find outliers, whether those outliers are meaningful or just statistical noise. The psychological hazard here is that humans interpret structure as intent. If something looks organized, we assume someone organized it. If something repeats, we assume it's trying to tell us something. This assumption works most of the time in human contexts, but it breaks down when applied to the universe. A crystal has structure. A spiral galaxy has structure. Neither was designed. So what would constitute a real message? Not intent necessarily, but information that changes what we know. A message might look like data behaving incorrectly, a light curve that doesn't match any comet model, a chemical composition that shouldn't exist outside a laboratory, a trajectory that requires forces we can't account for. The message wouldn't announce itself. It would just sit there in the numbers, waiting for someone to notice that the numbers don't add up. This is where things get uncomfortable, because if the numbers don't add up, you have two options. Option 1, your models are incomplete. This is the safe answer, the one that maintains the natural order of things. You go back, refine your calculations, account for variables you missed, and eventually the anomaly resolves into something explicable. Option 2, the numbers don't add up because something is making them not add up, because the data is being manipulated, because you're not observing natural phenomena, you're observing a signal disguised as natural phenomena. And then there's the possibility that terrifies information theorists more than anything else. The data reflects us, that the message, if there is one, isn't about the object at all. It's about what the object has observed, about us, about our broadcasts, our transmissions, our century of electromagnetic noise bleeding into space. What if 3i Atlas isn't sending a message? What if it's returning one? What if it's showing us our own reflection? Distorted by distance and time, proving that someone has been listening all along. That would change everything. Because it wouldn't just mean we're not alone. It would mean we've been studied, catalogued, understood in ways we don't understand ourselves. And if something out there knows us that well, knows what we broadcast and when and how, then silence isn't just a preference for them. It might be a survival strategy. One they're trying to teach us before it's too late. Which brings us to the first level of cosmic terror. Confusion. A message that contains no threat, no welcome, no explanation. Just a mirror held up to show us what we look like from outside, and the reflection is more disturbing than any monster could ever be. Part 3. Confusion. Level. A mirror message. Imagine this scenario. Astronomers analysing data from 3i Atlas notice something strange. The object's outgassing plumes vary in ways that correlate statistically with Earth's radio transmissions. Not perfectly, not in a way that screams artificial intelligence, but enough that the correlation is above noise, enough that it keeps showing up in different datasets, enough that you can't dismiss it as coincidence. The object appears to be echoing us. This is the confusion level, a message that contains no new information but proves prolonged observation. It's not hostile. It's not even communicative in the traditional sense. It's demonstrative. It says, I know you're there, I've been listening, here's proof. This could occur naturally, in theory. Electromagnetic radiation from Earth has been leaking into space for over a century. Radio waves from early broadcasts are now more than 100 light-years away, propagating outward in an expanding sphere. If an object happened to pass through that sphere, it could conceivably absorb some of that radiation and re-emit it in ways that produce correlations. Interstellar dust and plasma can act as natural reflectors and modulators of radio waves. The physics, isn't impossible. But the psychology is devastating, because if the correlation is real, it requires that something was positioned to observe us, not just recently, for decades, maybe longer, and it requires that whatever's doing the observing has been paying attention in silence, cataloguing our transmissions without ever responding. This is SETI's oldest nightmare, passive surveillance. Being watched is fundamentally different from being contacted. Contact implies a relationship, even an adversarial one. Surveillance implies asymmetry. It means someone has been studying you while you remained ignorant of their presence. It means they know more about you than you know about them. It means they've been making decisions about whether to reveal themselves, and so far the decision has been no. The idea of non-interactive intelligence is more disturbing than most people realise. We assume that if someone is out there, they'd want to talk. But what if they don't? What if observation is enough? What if they're cataloguing civilizations the way we catalogue stars, noting our existence in some vast database without any intention of making contact? We become specimens, objects of study, not peers, not threats, just data. The cosmic mirror concept flips the discovery narrative on its head. Usually, when we search for extraterrestrial intelligence, we're trying to learn about them, their technology, their culture, their biology. But a mirror message means we learn about ourselves, how we appear from outside, what our electromagnetic signature looks like from a distance, what patterns we create without meaning to. It's humbling in the worst way. We thought we were the observers. Turns out we're the observed. Consider what that does to our understanding of the universe. Every radio broadcast, every television signal, every radar ping we've sent into space for the past 100 years becomes part of our profile. A fingerprint we didn't know we were leaving. Scholars of Earth might study our transmissions the way we study ancient texts, parsing them for information about our technology, our conflicts, our entertainment, our fears. They could know more about human civilization from our leakage than most humans know about their own history. And they've said nothing. Made no attempt at contact, sent no response, just watched, recorded, maybe analysed. The silence is what makes it terrifying. If they're watching and not contacting, what does that tell you about their assessment of us? Are we not interesting enough? Not advanced enough? Too dangerous? Too primitive? The lack of response is itself a message, but we can't decode it because we don't know what criteria they're using. This level causes paralysis, not panic. Panic requires a clear threat. Paralysis comes from not knowing what to do with information that changes everything but demands nothing. Do you respond? Do you stay silent? Do you assume the observation is ongoing or was a one-time event? Every choice feels wrong because you don't have enough context to know what's safe. Some researchers would argue for immediate response, send a deliberate message back, acknowledge that we've noticed, open a dialogue. Others would argue for caution. If they haven't contacted us, maybe there's a reason. Maybe a response is dangerous. Maybe the smart play is to act like we didn't notice and see what happens next. But both positions assume we understand what's happening, and we don't. The mirror message doesn't tell us anything except that we've been seen. It doesn't explain why. It doesn't explain by whom. It doesn't tell us if being seen is dangerous or benign. It just confirms that the assumption we've operated under for centuries, that we're alone and unobserved in the cosmos, is false. Someone has been paying attention, and that changes the entire game. But confusion is only the first level. Because if the mirroring is intentional, it raises the question. Why bother? Why reveal surveillance unless you want something? Unless you're trying to send a warning? Unless the act of observation itself is supposed to tell us something we're not grasping? Which leads to the second possibility. The object isn't observing us, it's fleeing, and it wants us to know, because whatever it's running from might be coming for us next. Part 4. Natural or not? Mainstream as maverick interpretations. The official position is clear. NASA's Near-Earth Object Program classifies 3I Atlas as a comet. The European Space Agency's reports describe outgassing, consistent with sublimation of volatile ices. The International Astronomical Union lists it in the same catalogue as every other minor body we've ever tracked. There is no controversy. There is no debate. The object is natural. Science defaults to natural explanations for good reasons. Invoking the unknown without exhausting the known is lazy thinking. Every unexplained phenomenon in history that was later explained turned out to have a natural cause. Lightning isn't anger from the gods. Earthquakes aren't punishments. Comets aren't omens. They're weather, geology, and orbital mechanics. Assuming otherwise wastes time and credibility. But there are unresolved anomalies. Small ones. The kind that fit within the error bars of measurement but still make you look twice. Polarization data from certain observation windows doesn't quite match standard cometry models. It's close enough that you can invoke dust grain alignment or unusual surface textures, but it's off enough that it gets flagged in internal reviews. Compositional oddities exist too. The ratio of carbon dioxide to water vapour is within the range of known comets, but on the extreme end. Not impossible, just rare. History teaches us that natural doesn't always mean expected. When pulsars were first detected, they defied all existing models of stellar physics. The idea of an object spinning hundreds of times per second seemed absurd until we understood neutron stars. When fast radio bursts started appearing in the telescope data, they violated assumptions about what could produce that much energy in that little time. Now we have partial explanations, though the full picture remains unclear. Nature surprises us constantly. The boundary between science and speculation is not a wall, it's a gradient. At one end, you have peer-reviewed observations that replicate across multiple instruments. At the other end, you have hypotheses that can't be tested with current technology. In between, you have the grey zone where scientists ask questions without claiming answers, where they publish papers with titles like Possible Interpretations and Alternative Scenarios. Asking questions isn't conspiracy, it's methodology. Science progresses by challenging models, by finding edge cases that don't fit, by admitting when we don't know something. The problem arises when speculation gets stripped of its caveats and presented as fact. When a scientist says we can't rule out the possibility, and a headline reads, "Scientists confirm," the telephone game between research and public understanding introduces distortion at every step. Careful skepticism looks like this, acknowledging that most anomalies resolve into natural phenomena once you have better data, while remaining open to the possibility that some don't. Sensationalism looks like this, treating every unexplained data point as evidence of intelligence and ignoring all the explained data points that surround it. One is intellectually honest. The other is profitable. Unknown, natural processes are the real frontier. The universe operates on scales and in conditions we can't replicate in laboratories. We've never seen an interstellar comet up close. We've never sampled material that formed in a different stellar system. Every assumption we make about what's normal comes from a sample size of 1, our solar system. 3i Atlas could be doing something perfectly natural that we've just never witnessed before. The challenge is distinguishing between "we don't understand this yet" and "this can't be explained naturally." Those sound similar but have profoundly different implications. The first means we need more data. The second means we need to reconsider fundamental assumptions about what's possible. Scientists are trained to exhaust the first option before even considering the second. But exhausting natural explanations takes time. You need observations across multiple wavelengths. You need spectroscopic analysis with high signal-to-noise ratios. You need trajectory data refined over weeks or months. You need computer models that account for every known force. Only after all of that fails to explain what you're seeing can you legitimately say the phenomenon is anomalous. And even then you have to consider observer error, instrumental artifacts and mathematical mistakes before invoking anything exotic. Uncertainty is fuel for narrative fear. When you don't have a complete explanation, your brain fills in the gaps, and human brains are terrible at filling gaps with boring possibilities. We don't imagine unusual but natural dust grain alignment. We imagine surveillance. We imagine intent. We imagine danger. Because stories about mundane misunderstandings don't keep you awake at night. Social media accelerates this process. An astronomer mentions an unexplained data point in a conference presentation. Someone live tweets it. The tweet gets shared with added speculation. By the time it reaches the general public, it's transformed from anomaly requiring further study into proof of alien technology. The researcher then has to spend time issuing corrections instead of doing research. The cycle repeats with every new observation. This creates a perverse incentive structure. Scientists who refuse to speculate publicly get ignored. Scientists who speculate carefully get misquoted. Scientists who speculate carelessly get amplified. The ones who benefit most are the ones willing to make the boldest claims with the least evidence. And that's exactly backwards from how science should work. But when enough anomalies cluster in one place, when the list of things that need explaining grows longer than the list of things already explained, curiosity mutates into suspicion. You start wondering if the lack of a clear explanation is itself information. You start asking not just what the object is, but what it's doing here. And why now? Why this particular trajectory at this particular time? Coincidence or something else? Part 5. Controversy. Primer. Speculation isn't fringe anymore. The conversation shifted after Oumuamua. Before 2017, suggesting that an interstellar object might be artificial was career suicide for an astronomer. After Oumuamua's flyby, it became a discussable hypothesis, not a dominant one, not one that most scientists endorse, but one that appears in papers published by reputable institutions. Avi Loeb, chair of Harvard's astronomy department, proposed that Oumuamua could be a light sail, a thin reflective surface pushed by radiation pressure. His reasoning focused on the object's non-gravitational acceleration and its unusual shape. Mainstream astronomers pushed back, offering alternative explanations involving outgassing and fragmentation. The debate didn't resolve. It just exposed the fact that we don't have enough data to rule anything out definitively. This matters because it cracked open a door that had been nailed shut. Speculation about artificial objects in space was previously relegated to science fiction and fringe websites. Now it appears in journals like the Astrophysical Journal Letters. The methodology is careful, the language is hedged, but the ideas are there, in print, with institutional affiliations attached. Why do mainstream journals publish speculative frameworks? Because the scientific method requires considering all possibilities that fit the data. If you can't explain something with known processes, you're obligated to consider unknown ones. That includes intelligence. Excluding it a priori is bias. But including it requires extraordinary care, because the history of false positives in this field is long and embarrassing. The Drake equation tried to quantify the number of detectable civilizations in the galaxy. Frank Drake developed it in 1961 as a framework for discussion, not a calculation with real numbers. But people treat it like a formula that produces answers. They plug in optimistic values and conclude the galaxy must be teeming with life. They plug in pessimistic values and conclude we're alone. The equation doesn't tell you which is true, it tells you what factors matter. And one of those factors is how long technological civilizations remain detectable. If civilizations only broadcast for a few centuries before going quiet, either through extinction or intentional silence, then the detection window is narrow. We might be surrounded by civilizations that existed millions of years ago, or will exist millions of years from now, but overlap is rare. This is one solution to the Fermi paradox. We're not detecting anyone because timing matters as much as distance. Speculation spreads faster than corrections. A paper proposing an unconventional explanation gets picked up by news outlets and presented without caveats. The headline reads, "Harvard professor says alien probe visited Earth." The paper actually says, "We cannot exclude the possibility that objects of artificial origin could be detected through anomalous acceleration." Those are not the same statement. But the correction never gets the same reach as the initial claim. Media amplification exists in tension with scientific caution. Journalists need stories that engage readers. Scientists need accuracy that withstands peer review. The incentives don't align. This creates a feedback loop where researchers become more reluctant to speculate publicly, which makes the few who do speculate look like outliers, which makes their speculation seem more extreme than it is. Speculation thrives in informational gaps. When you don't have high-resolution images, when you can't land a probe, when the object is millions of miles away and moving fast, every measurement is incomplete. Incomplete data means multiple interpretations fit, and when multiple interpretations fit, people gravitate toward the most interesting one, not the most likely. The most interesting. There is no evidence of artificial origin for 3I Atlas. That needs to be stated plainly. The observations we have are consistent with a natural comet, but consistency with natural processes doesn't equal proof of natural origin. It just means we can't tell the difference yet, and that ambiguity is where speculation lives. There's also no precedent for certainty. We've never encountered something like this before. We don't have a control group. We don't have comparison cases. We're trying to figure out what's normal for interstellar objects when we've only confirmed 3 of them. That's not enough data to build reliable models. The problem with establishing baselines is that baselines require repetition. You need to observe multiple instances of a phenomenon under different conditions before you can say what's typical. 3 interstellar objects don't give you that. especially when all three have been different from each other. Oumuamua was elongated and accelerating. Tuibrusov looked like a regular comet. 3I Atlas falls somewhere in between. The variance is high enough that you can't define normal yet. Framing speculation as a thought experiment is useful. It lets us ask what if without claiming what is. What if an object like this were artificial? What would we expect to see? How would it differ from natural phenomena? What tests could we run? These questions aren't endorsements of alien probes. They're exercises in preparedness, because if something genuinely artificial ever does show up, we need to have thought through how we'd recognise it. The challenge is that artificial objects might intentionally mimic natural ones. If you're crossing interstellar space and you want to avoid detection, you'd design your craft to look like a comet or asteroid. You'd use materials and trajectories that blend in. You'd minimise energy emissions. You'd coast on momentum whenever possible. This means the very signatures we'd look for to identify artificial objects might be deliberately absent. So if the object isn't hostile, if it's not a probe, if it's not sending greetings, then why would it come at all? That question pulls us into the second tier of terror. Maybe it didn't come for us. Maybe it came from something. Maybe it's running. And if something advanced enough to cross interstellar space is fleeing, what could possibly scare them enough to run? Part 6. Distress Level. A refugee from the unknown. The distress level doesn't start with a message that says we are coming. It starts with one that says we are running. This shifts the entire psychological framework. Suddenly the visitor isn't the threat. The visitor is the warning. Refugee scenarios appear constantly in astrobiology fiction because they tap into something primal. The fear of pursuit. The fear of something worse behind you. If an advanced civilization capable of interstellar travel is fleeing, what could possibly scare them? And more importantly, is it following? Real astrophysical dangers exist that could force evacuation. Gamma-ray bursts are the most lethal phenomena in the universe. When a massive star collapses into a black hole, it can release more energy in 10 seconds than the sun will emit in its entire lifetime. If that beam is pointed at your planet, it strips away your atmosphere and bathes your surface in radiation that sterilizes everything. There's no defense. You either weren't in the way, or you're dead. The terrifying thing about gamma-ray bursts is the lack of warning. Light travels at the same speed as the destruction. By the time you detect the burst, you're already being hit. There's no time to evacuate, no time to prepare. But if a civilization had sophisticated enough sensors, they might detect the precursor signs. The collapsing star before it bursts, the gravitational waves that arrive seconds earlier. That could give them hours or days of warning. Just enough time to run. Stellar flares from red dwarf stars can achieve similar results on a smaller scale. Many potentially habitable exoplanets orbit red dwarfs because they're the most common type of star. But red dwarfs are volatile. They produce super flares that can erode atmospheres over millions of years. Civilization on such a world might have centuries to prepare, but eventually, they'd need to leave. Rogue black holes are more speculative but no less terrifying. Black holes don't emit light, so you don't see them coming. If one passed through a solar system, it would gravitationally disrupt planetary orbits, potentially flinging worlds into interstellar space or sending them crashing into their star. An advanced civilization with good enough sensors might detect the gravitational anomaly decades in advance, just enough time to evacuate. But here's what keeps cosmologists awake. There are threats we haven't imagined yet. Phenomena that don't exist in our current models of physics. Dangers that emerge at scales or in conditions we've never observed. The universe is under no obligation to limit its catastrophes to things we've theorized about. There could be stellar processes, galactic events, or cosmological transitions that make gamma-ray bursts look manageable by comparison. Why would refugees flee silently? Because noise attracts attention. If you're running from something, the last thing you want is to announce your position to whatever's chasing you. You minimize your electromagnetic signature. You coast on momentum rather than using energy-intensive propulsion. You blend in with natural objects as much as possible. A comet is perfect camouflage. Trajectory implications matter here, though claiming intent requires more data than we have. If 3I Atlas were truly fleeing something, its velocity vector should point away from a specific region of space. Astronomers can trace its path backward, calculating roughly where it came from. So far, those calculations show it originated from somewhere in the general direction of the constellation Cassiopeia. That tells us almost nothing. Cassiopeia covers a huge swath of sky containing millions of stars, but if the trajectory were refined and pointed to a specific stellar system, that would change things. Imagine receiving confirmation that 3I Atlas originated from a star system we've studied. One where we've detected exoplanets in the habitable zone. One that seemed stable, unremarkable, a place where life could theoretically evolve. And now something from that system is racing away at interstellar velocities, taking a trajectory that happened to bring it past Earth. Coincidence? Or a calculated path that takes it as far from its origin point as physics allows? The psychological impact of a refugee scenario is the fear of an unseen third party. You're not scared of the visitor. You're scared of what made the visitor run. It's the same fear you feel when someone runs past you in a panic, and you don't know what they're running from. Your instinct is to run too. But you don't know which direction is safe. Predator-prey cosmology is a framework that reframes the Fermi paradox. Instead of asking why we haven't found anyone, it asks why we haven't been found. The answer could be that successful civilizations learn to hide. They stop broadcasting. They minimize their presence. They go dark, and the ones that don't go dark disappear. The horror here is asymmetry. In a predator-prey cosmos, you don't know if you're predator, prey, or irrelevant. You don't know if being loud is dangerous because you'll attract predators, or if being quiet is dangerous because you won't attract allies. Every choice is a gamble with incomplete information. And there's another layer to this. If 3I Atlas is a refugee, it means someone survived long enough to evacuate. Long enough to build interstellar capability. Long enough to recognize the danger and respond. But where did they go? If they're running, do they have a destination? Or are they just putting distance between themselves and whatever they're fleeing, hoping that space itself provides safety? The object we're observing might not be a ship. It might be a lifeboat, the remnant of something larger that didn't make it. But there's a level beyond distress, a message that doesn't just imply danger, a message that specifies it, not through description, but through instruction. Stop broadcasting. And the reason becomes clear when you understand what's listening. Part 7. Anomalies that won't die. Complex chemistry and behaviour. Comets are dirty snowballs. That's the simplest description. A mixture of water ice, frozen gases like carbon dioxide and methane, and dust particles made of silicates and organic compounds. When a comet gets close to the Sun, the ice sublimates directly from solid to gas, creating the coma and tail we associate with these objects. This process is well understood for comets that formed in our solar system. Interstellar chemistry is expected to be weird. A comet that formed around a different star experienced different temperatures, different radiation environments, different elemental abundances. The proportions of various ices depend on where the comet condensed in its birth system. A comet from a carbon-rich system might have more organic compounds. One from a system with a massive planet might have been gravitationally perturbed before it fully formed, giving it an unusual structure. The carbon dioxide to water ratio in 3I Atlas is within known ranges but on the high end. Most solar system comets show water as the dominant volatile. 3I Atlas shows CO2 as more prominent in certain outgassing episodes. This isn't unprecedented. Comet 29 P. Schwarzmann-Wachmann 1 exhibits similar behaviour. But it's uncommon enough that it gets noted in observational reports. What makes this interesting is consistency. When you observe the same anomaly across multiple observation windows, using different instruments, from different locations, it starts looking less like instrumental error and more like a real feature. The CO2 dominance in 3I Atlas persists. It's reproducible, which means it's telling us something about either the object's formation environment or its current behaviour, or possibly both. Jet behaviour adds another layer. When comets outgas, they don't do it uniformly. Localised vents on the surface produce jets that can change the object's rotation and create asymmetric forces. These non-gravitational accelerations are normal, but predicting them requires knowing the surface structure in detail, which we don't have for 3I Atlas. So when the object accelerates slightly in ways that don't match initial models, it's not shocking, it's expected uncertainty. But here's where it gets complicated. The jets from 3I Atlas don't follow the pattern you'd expect from a simple rotating body with random surface features. They seem to activate at specific points in the orbit. Not random points, specific ones. This could be because certain areas of the surface only heat up enough to outgas when they reach particular distances from the sun. Perfectly natural. But it could also mean the surface has structure we're not accounting for. Possibly natural structure, possibly not. Anomalies do not equal artificial. This point can't be stressed enough. Finding something unusual doesn't mean you've found something engineered, it means you've found something you need to study more. The universe is full of natural phenomena that violate our assumptions because our assumptions were incomplete. Tabby's star is the classic example, KIC 8462852 officially. For years it showed bizarre dimming patterns that didn't match any known astrophysical process. Speculation ran wild. Alien megastructures, Dyson swarms, advanced civilizations harvesting stellar energy. Then more observations came in, and the likely explanation emerged. A debris field, probably from a shattered comet, creating irregular eclipses. Natural. Disappointing to some, but ultimately explicable. But anomalies do equal narrative instability. When you can't give a definitive explanation, people fill in their own. And the longer anomalies persist across multiple objects, the more they start to feel like a pattern rather than noise. Oumuamua had anomalies. 2i Borisov had fewer, which reassured people. Now 3i Atlas has its own set. You start wondering if interstellar objects are just intrinsically weird, or if we're missing something systematic. Observer bias matters too. If you expect something to be strange, you pay closer attention to the strange parts and downplay the normal parts. This is why peer review exists. To catch the moments when a researcher becomes too invested in an anomaly to evaluate it dispassionately. But peer review also means that anomalies which survive scrutiny have to be taken seriously. Instrumentation limits are real. We're observing 3i Atlas from tens of millions of miles away. The best telescopes on Earth can barely resolve it as more than a point of light. Space-based telescopes have better resolution but limited observation windows. We're reconstructing its properties from indirect measurements, like trying to identify an animal by studying its shadow. Spectroscopy gives you chemistry but not structure. You know what elements are present. You don't know how they're arranged. Photometry gives you brightness changes but not causation. You know it's getting brighter or dimmer. You don't know why. Astrometry gives you position but not intent. You know where it's going. You don't know if that's deliberate. Edge cases in astrophysics are where new physics gets discovered. Pulsars were an edge case. Black holes were an edge case until we detected them directly. Fast radio bursts are still an edge case we're trying to understand. Dismissing edge cases too quickly means missing opportunities. Obsessing over them too much means wasting resources on statistical flukes. The universe does not owe us clarity. That's the uncomfortable truth. Objects can be ambiguous. Data can be incomplete. Phenomena can exist that we don't have the tools to explain yet. And being comfortable with that uncertainty is part of doing science honestly. But it doesn't make the uncertainty less unnerving, because uncertainty creates space for imagination. And human imagination, when faced with cosmic mysteries, rarely settles on boring explanations. Part 8. The Hidden Angle. SETI. Silence and Survival. The Fermi paradox is older than most people realise. Enrico Fermi asked the question in 1950 while discussing the probability of extraterrestrial civilizations with colleagues. If intelligent life is common, and if some civilizations develop interstellar travel, then where are they? Why haven't we seen evidence of galactic colonization? The galaxy is billions of years old. Even slow expansion should fill it by now. Dozens of proposed solutions exist. Maybe life is rare. Maybe intelligence is rare. Maybe technological civilizations destroy themselves before they expand. Maybe they're out there, but we're not looking in the right way. Each solution has proponents and problems. None are definitive. The Great Silence is the observational manifestation of the paradox. We've been listening for decades. SETI programs have scanned thousands of stars. We've found nothing. No radio signals, no laser pulses, no megastructures blocking starlight. The universe appears empty of technological civilizations, at least ones that broadcast. But what if the silence isn't absence? What if it's strategy? That's where dark forest theory enters the conversation. The name comes from a science fiction novel by Liu Cixin, but the concept predates the book. It's based on game theory applied to cosmic scales. The universe is a dark forest. Every civilization is an armed hunter moving silently through the trees. You don't know if other hunters are friendly or hostile. You don't know their capabilities or intentions. So you stay quiet. You listen. And if you detect someone else, you face a terrible choice. Do you risk contact? Do you reveal yourself and hope they're friendly? Or do you eliminate the potential threat before it can eliminate you? Because once you know they exist, they might know you exist too. And the first civilization to strike has an enormous advantage. This creates a cosmic Mexican standoff where everyone stays hidden, because revealing yourself might be fatal. This is a risk model, not a proven fact. It's a thought experiment about what rational civilizations might do given certain assumptions. The first assumption is that resources are valuable and potentially scarce. The second is that civilizations compete for resources. The third is that you can never be sure another civilization won't attack you, even if they seem peaceful. The fourth is that destroying another civilization is easier than defending against one. Given these assumptions, the rational strategy is silence and preemptive strike if you detect others. Whether these assumptions hold for non-human intelligence is unknown. Maybe alien civilizations are inherently cooperative. Maybe they've solved scarcity. Maybe their psychology doesn't include paranoia or aggression. Or maybe it does, and they've learned through bitter experience that loudness equals death. Silence could be strategic in ways that have nothing to do with deliberate hiding. Maybe advanced civilizations simply stop using technologies that leak electromagnetic radiation. They switch to more efficient communication methods that don't broadcast into space. Quantum communication is point-to-point with no interception possible. Contained networks don't emit stray signals. As technology improves, the signature shrinks. Eventually you become invisible not because you're trying to hide, but because your technology is so refined it produces no waste. Broadcast versus listen, civilizations create a selection bias in what we detect. If most civilizations eventually go quiet, either through extinction or technological maturation, then the ones we'd most likely detect are either very young or very reckless. Young civilizations haven't learned the danger yet. Reckless ones don't care. Both are temporary states. You either mature and go quiet, or you get eliminated by something that noticed your noise. Technological adolescence is the period when a civilization is loud but vulnerable. You have radio, you have nuclear weapons, you have satellites and space stations, but you don't have interstellar travel. You don't have planetary defense against external threats. You're shouting into the galaxy without knowing who's listening, and you're too primitive to protect yourself if the wrong entity hears you. Earth has been in technological adolescence for about a century. That's nothing on cosmic timescales, but it's also the most dangerous period in any civilization's history. You're advanced enough to be noticeable, but not advanced enough to survive contact with something more advanced. You're a child wandering through a forest, calling out to see if anyone's there, unaware that predators exist. Earth is unusually loud compared to what a cautious civilization would allow. We're not trying to hide. We're not even trying to be quiet. We light up the night side of our planet with so much artificial light that it's visible from space. We fill the radio spectrum with communication signals. We've detonated thousands of nuclear weapons, each one releasing isotopes detectable across interstellar distances. We've been drawing attention to ourselves for decades without considering whether that's wise. The Arecibo message in 1974 was deliberate broadcast, a coded message sent toward the globular cluster M, 25,000 light-years away. It contained information about humanity, our chemistry, our solar system, even a crude image of a human. The message won't arrive for millennia, and even if someone receives it and responds immediately, we won't hear back for 50,000 years. But the message is out there, permanent, irrevocable. Framing silence as evolved behaviour suggests that the civilizations we don't detect aren't absent. They're careful. They learned something we haven't learned yet. They figured out that survival requires restraint. And if that's true, then the question becomes, what taught them? What did they encounter that made silence necessary? Was it a close call? A near miss with something dangerous? Or was it something worse? Something they barely survived? And if that's the lesson they learned, if silence equals survival, then maybe that's what they're trying to tell us. Maybe that's the only message worth sending across interstellar distances. Not greetings, not information exchange, just a warning. Be quiet, stop broadcasting before something hears you. Part 9. Conspiracies, Unknowns, and Public Mistrust. Reddit threads about 3i Atlas run hundreds of comments deep. Amateur astronomers post their own observations, comparing notes on brightness fluctuations and trajectory calculations. Some of it is solid work. People with backyard telescopes and CCD cameras can contribute meaningful data when enough of them coordinate. But the signal-to-noise ratio is terrible. Misinterpretation of brightness changes is common. Comets rotate. As they rotate, different parts of their surface reflect sunlight at different angles. This creates variability in brightness that's perfectly predictable if you know the rotation period and surface features. But if you don't know those things, the variations look random, and random variations trigger pattern-seeking behavior. People start seeing pulses where none exist. Someone posts a light curve showing regular dips. Another person points out those dips correspond to Earth day intervals. Speculation erupts. Is it signaling? Is it timed to our rotation? The more prosaic explanation, that the observer was taking measurements at the same time each day and introducing observational bias, gets lost in the noise. The exciting explanation spreads. The boring truth doesn't. Observational artifacts are another issue. Atmospheric turbulence affects ground-based observations. Satellite trails cross the field of view. Cosmic rays hit camera sensors and create false signals. Every amateur astronomer learns to filter these out, but it takes experience. Newcomers capture anomalies that aren't real and share them online, where they get amplified by people who don't know the difference. Velocity misunderstandings generate their share of confusion. Interstellar objects move fast relative to the Sun, but that doesn't mean they're accelerating. Their speed is constant in the absence of forces acting on them. When people see that 3i Atlas is moving at tens of kilometers per second, they assume propulsion. But gravitational slingshots around massive objects can achieve those speeds without engines. Jupiter alone can boost an object's velocity by dozens of kilometers per second if the trajectory is right. Misinformation propagates through social networks faster than facts. A misleading claim gets shared thousands of times before anyone fact-checks it. By the time a correction is posted, the original claim has reached people who'll never see the rebuttal. This isn't unique to astronomy. It's a structural problem with how information spreads online. Novelty gets amplified, correction gets ignored, but distrust of institutions exists for real reasons. Scientists sometimes communicate poorly, using jargon that alienates non-specialists. Press releases get written by public relations departments that prioritize engagement over accuracy. Governments have histories of classifying information about aerial phenomena, creating suspicion about what else might be hidden. All of this erodes trust. The Pentagon's UAP reports added fuel to this fire. For decades, the government dismissed UFO sightings as misidentifications, hoaxes, or delusions. Then in 2021, official reports acknowledged that some aerial phenomena remain unexplained. This validated people who'd been claiming cover-ups for years. It didn't prove aliens, but it proved that dismissals had been premature. Trust, once broken, is hard to rebuild. Transparency challenges are genuine. Some observations are classified because they come from military sensors. Some data isn't published immediately because researchers want to verify it before releasing findings. These delays are professionally responsible, but they create informational voids that get filled with speculation. Nature abhors a vacuum. So does the internet. Secrecy accusations emerge whenever information is incomplete. If scientists can't explain something fully, people assume they're holding back. If governments delay releasing data, people assume it's proof of something extraordinary. The absence of information gets interpreted as confirmation rather than uncertainty. This is a cognitive error, but it's a predictable one. Public fear is often rational uncertainty. People know they don't have access to all the data. They know that major discoveries take time to verify and announce. They know that by the time information reaches them, it's been filtered through multiple layers. So when something unusual appears in the sky, and the official explanation sounds incomplete, skepticism isn't irrational. It's reasonable doubt. The problem is when reasonable doubt metastasizes into unreasonable certainty. When we don't know yet becomes they're lying to us, becomes it's definitely aliens and they're covering it up. That progression happens fast online because confirmation bias is powerful. People seek out information that supports what they already believe and ignore information that contradicts it. Even false signals reveal true anxieties. When someone interprets a natural phenomenon as artificial, They're expressing a belief that contact is possible and imminent. When someone distrusts official explanations, they're expressing a belief that they're not being told the full truth. These beliefs might be wrong in specific cases, but they're not absurd in general. Contact is possible. Institutions do withhold information. The question is whether this specific case is an example. And there's a deeper anxiety underneath all of this. The fear that we're not prepared. That if something significant happens, whether it's first contact or a genuine threat, the institutions we rely on won't handle it well. That we'll find out too late. That decisions will be made without public input. That by the time ordinary people learn what's happening, it'll already be over. This fear isn't entirely unjustified. History provides plenty of examples of institutional failure, which leads to the question that bridges all three levels of terror. Are we looking at a warning? Not a greeting, not a threat, but an urgent message that we've already missed the point? Because warnings only work if you recognize them as warnings, and if you're busy debating whether something is natural or artificial, you might miss the fact that it's neither. It's educational. It's trying to teach you something you need to know before it's too late. Part 10. The tension climbs. Are we looking at a warning? Let's summarize where we are. We've established that 3-eye atlas is observable, that it exhibits behaviors consistent with natural phenomena, and that anomalies exist within error margins. We've explored how messages could arrive not as deliberate transmissions, but as observable patterns. We've examined the confusion level, where mirroring proves surveillance. We've walked through the distress level, where the visitor is a refugee fleeing something worse. And now we're approaching the edge of the third level, where the message isn't about the sender at all, it's about us. The hypothesis goes like this. What if certain behaviours we observe aren't meant to convey information about the object's origin or composition? What if they're meant to convey instructions, not complex instructions, not detailed maps or mathematical proofs, just a simple directive encoded in the simplest possible way? A warning. Evolutionary survival messaging would be minimal by necessity. If you're trying to communicate with a species you know nothing about, you can't use language. You can't assume shared cultural references. You can't even assume they process information the same way you do. So you'd use the most basic form of communication, deviation from expected patterns. You do something that looks wrong according to natural laws, something that can only be interpreted as deliberate. Think about what that means in practice. A comet that outgasses at intervals that correlate with prime numbers, a trajectory that adjusts in ways requiring forces we can't account for, chemical signatures that oscillate between states faster than thermodynamics should allow. Nothing elaborate, nothing that screams artificial intelligence sent this. Just enough wrongness that scientists can't dismiss it, can't explain it away, can't stop thinking about it. The message is in the impossibility itself. The challenge with minimal messaging is ambiguity. The simpler your message, the more interpretations it allows. If you just flash a light 3 times, does that mean danger, hello, look here, or something else entirely? Context matters, but context is exactly what you don't have when communicating across species that evolved independently. So minimal messages have to rely on universal concepts, mathematics, physics, things that should be constant regardless of biology or culture. But even universal concepts can be misunderstood. The Arecibo message sent in 1974 used binary code to represent numbers, chemical formulas, and crude images. We assumed any technological civilization would understand binary. We assumed they'd recognize DNA structure. We assumed they'd interpret the patterns the way we intended. But what if they don't? What if their mathematics developed differently? What if they see our message and interpret it as noise, or worse, as a threat? Why would warnings be minimal? Because elaborate messages require shared context. They require that both sides understand the code, the syntax, the semantic framework. But a warning only needs to say stop, change course. Don't do that. The content of the warning is less important than the fact that a warning was issued. If you see someone waving their arms frantically at you while you're walking, you stop. You don't need to understand their language to know something is wrong. The urgency transcends translation. The same principle applies at cosmic scales. If you want to warn a civilization about danger, you don't need to explain the nature of the danger in detail. You just need to convey urgency and direction. Stop broadcasting. Be quiet. Hide. The specifics of why can come later if there's time. The immediate goal is behavior change. Get them to stop doing the thing that's putting them at risk. Ambiguity could be intentional. If you want to warn someone without revealing too much about yourself, you make the warning unclear enough that it can't be traced back definitively. You give them enough information to change behaviour, but not enough to locate you. This is especially important if the danger is detection itself. If being found is the risk, then your warning can't make you findable. You have to balance urgency with anonymity. This creates a paradox. The more specific your warning, the more useful it is, but the more it reveals about you. The more you explain about the danger, the more you expose about what you know and how you know it. So you stay vague, you hint, you create just enough disturbance in the data that someone paying attention will notice something's wrong, but not so much disturbance that predators notice you're the one doing the warning. The cost of misinterpretation is extinction level. If a civilization misreads a warning as a greeting, they might respond in ways that escalate danger. They might broadcast replies. They might send detailed information about their location, their capabilities, their resources, all the things a predator would want to know. If they misread silence as absence, they might continue behaviours that attracted attention in the first place. Keep broadcasting, keep being loud, keep making themselves targets. The margin for error is zero. You can't afford to get this wrong. History is full of misinterpreted warnings on smaller scales. Animals that display warning coloration to signal poison sometimes get eaten anyway by predators that don't recognise the pattern. Fire alarms that sound too often get ignored when there's a real fire. The boy who cried wolf loses credibility until the wolf actually comes. Warnings only work if they're received correctly, interpreted correctly, and acted upon correctly. Any failure in that chain means the warning was worthless. What would we warn about if we discovered a young civilization? Think about it. If Earth's astronomers detected techno-signatures from an exoplanet, and we knew something about the galaxy that they didn't, what would we try to communicate? We'd tell them to be careful. We'd tell them that broadcasting has consequences. We'd tell them that the universe is more dangerous than they think. Not because we're hostile, but because something else is. We'd want them to know that their radio signals are travelling outward at the speed of light, announcing their presence to anyone within range. We'd want them to know that visibility might equal vulnerability. We'd want them to understand that the great silence might not be absence but strategy, that the civilizations that survive are the ones that learn to hide, and we'd want them to learn this lesson before it's too late, before they attract the wrong kind of attention. This raises an interesting philosophical question. Do you have an obligation to warn others of danger, even if warning them might draw attention to you? If you've survived by being quiet, and you encounter someone being loud, do you risk your own safety to tell them to shut up? Or do you stay hidden and hope they figure it out on their own? Different ethical frameworks would answer differently. Utilitarian ethics might say yes, warn them, because the benefit of saving a civilization outweighs the risk to yourself. Deontological ethics might say you have a duty to prevent harm when you can, but survival ethics, the kind of ethics that evolves when existential threats are real and constant, might say no. Don't risk yourself for strangers. Your survival is paramount. Let them learn the hard way, the way you did. The galaxy is full of hard lessons. Not your responsibility to teach them all. Irreversible knowledge is a concept that applies here. Once you learn something, you can't unlearn it. Once you know that silence might be survival, you can't go back to assuming the universe is empty. The warning changes you even if you don't fully understand it. You become cautious in ways you weren't before. Your behaviour shifts. You start questioning assumptions you'd never questioned before. You second-guess decisions that once seemed obvious. This is the power of doubt. Before the warning, you operated with certainty. The universe was empty, or at least uninhabited by anything dangerous. You could broadcast freely. You could explore openly. You could assume that first contact, if it happened, would be benign or at least neutral. After the warning, all of that disappears. You don't know what's out there. You don't know if you're safe. Every transmission becomes a risk calculation. Every signal you send might be the one that gets you noticed. So imagine this. 3i Atlas arrives. It does nothing overtly threatening. It follows a trajectory that brings it close to Earth at a specific time. It exhibits chemical and physical properties that are almost but not quite explicable. It creates just enough doubt that astronomers keep analysing, keep debating, keep publishing papers. And in doing so, it gets humanity's attention. Getting attention might be the entire point. Not to announce themselves, but to make us think, to make us question whether we're alone. to introduce doubt where certainty existed before. Because once you doubt you're alone, you start behaving differently. You become more aware, more cautious. You start thinking about what messages you're sending. You start wondering who might be listening. The beauty of this approach is that it requires no complex technology, no radio transmission, no laser communication, no mathematical proofs encoded in trajectories. Just an object that's weird enough to make scientists uncomfortable. Weird enough to generate papers and conferences and public interest. Weird enough that humanity collectively starts asking questions it wasn't asking before. And those questions change us. They change our relationship with the cosmos. We stop assuming we're alone. We stop assuming we're safe. We start considering possibilities we dismissed as science fiction. What if someone's watching? What if broadcasting is dangerous? What if we need to be more careful about what signals we send into space? The warning works not through explicit instruction, but through implication, through making us aware of possibilities we'd ignored. The scariest message wouldn't ask anything of us except silence. It wouldn't demand submission or tribute. It wouldn't threaten invasion. It would just say, "You've been noticed. Stop making noise, because there's something out there that listens for noise, and you don't want to meet it." That's the dark forest level. And it's worse than war because war has rules. War has objectives. War has victory conditions and defeat conditions. War ends. One side wins, the other loses. Terms are negotiated, treaties are signed. Life continues in some form. But hiding from an invisible predator is a permanent condition. You never know if you're safe. You never know if the danger passed or if it's still out there waiting, watching, listening. You never know if being quiet is enough, or if being noticed once means you're marked forever. Maybe the predators catalogue every loud civilization they detect, prioritizing targets based on technological level and resource value. Maybe they wait until you're more developed before harvesting. Maybe they're patient on timescales that make centuries seem like seconds. The uncertainty becomes a prison. You're trapped not by walls, but by fear of what might be outside those walls. And the worst part? You built the prison yourself by being loud in the first place. Every radio broadcast, every television signal, every radar pulse for the past 100 years has been expanding outward at the speed of light. You can't take them back. You can't recall them. They're out there, announcing Earth's presence to anyone within listening range. The only question is whether anyone's listening and what they'll do if they hear you. This is the existential weight of the warning. It tells you that the rules have changed, that assumptions you based your entire civilization on might be wrong, that the universe isn't the benign, empty place you hoped it was, that there are consequences for actions you took in ignorance, and those consequences might be coming, might already be on their way, and there's nothing you can do except go quiet and hope that's enough. Hope you're not already too late. Part 11. Dark Forest Level, Stop Broadcasting. Here's the message in its simplest form. Stop broadcasting. Not we come in peace. Not prepare for contact. Not surrender or die. Just two words, encoded in whatever minimal way is necessary to convey urgency without complexity. Maybe it's a repeating pattern in outgassing that can't occur naturally. Maybe it's a trajectory adjustment timed to coincide with Earth's position that requires intelligence to execute. Maybe it's something we haven't noticed yet because we're not looking for instructions. We're looking for information. Why is this worse than a declaration of war? Because war gives you something to fight. War tells you who the enemy is, what they want, and how they plan to take it. You can prepare. You can strategize. You can mobilize. You can die knowing why. But this message doesn't give you an enemy. It gives you a constraint to stop broadcasting. And the reason isn't explained because explaining would itself be broadcasting. The message is recursive. Its meaning depends on obeying it immediately. The implication of predators is unavoidable. If someone is warning you to be quiet, it means noise is dangerous. And if noise is dangerous, something must be hunting the noisy. You don't know what it is. You don't know where it is. You don't know its capabilities or its motivations. You only know that someone who survived long enough to reach you thinks you're in danger, and their solution is silence. Noise-based detection is how we search for technosignatures. We look for electromagnetic emissions that don't match natural sources. We scan for laser pulses, radio signals, and artificial chemicals in exoplanet atmospheres. Narrowband radio signals are particularly suspicious because natural processes tend to produce broadband noise. A signal concentrated in a narrow frequency range suggests a transmitter, an oscillator, something designed. If we can detect civilizations this way, then so can others. This creates a fundamental asymmetry in the cosmos. Detection is passive. You can listen without revealing yourself. But broadcasting is active. Every signal you send is an announcement. Every transmission is a billboard saying here we are to anyone with the right equipment. The listener has all the advantages, the broadcaster has none. Connecting this to evolutionary silence creates a chilling framework. Civilizations that broadcast go extinct. Civilizations that don't broadcast survive. Over millions of years, natural selection favours the quiet ones. Not because quiet civilizations are inherently superior, but because loud ones get eliminated. The selection pressure is external. Something in the galaxy removes broadcasters. What remains is a universe full of civilizations that exist but don't announce themselves. Cosmic hunter logic is straightforward. If you're a predatory civilization harvesting resources from other civilizations, you don't waste energy searching randomly. You wait for prey to reveal themselves. You monitor the galaxy for anomalous signals. When someone broadcasts, you note their location. You assess their technological level. You determine whether they're worth exploiting. Young civilizations are easy targets. They don't have defenses. They don't expect attack. They're loud precisely because they're naive. This model assumes certain things about alien psychology. It assumes that resource competition exists. It assumes that some civilizations prioritize expansion and acquisition. It assumes that interstellar travel is possible, but costly enough that you'd target your efforts. These assumptions might be wrong, but if they're even partially right for even one predatory civilization, then everyone else needs to hide. One wolf in the forest means all the deer stay quiet. Earth's century of broadcasts is our vulnerability. Radio and television signals have been leaking into space since the 1920s. We've sent deliberate messages via SETI projects like the Arecibo transmission in 1974. Those signals are out there, they can't be recalled. They're expanding outward at the speed of light, creating an ever-growing sphere of revelation. Anyone within 100 light-years knows we're here. Anyone within 50 years of travel time could reach us within a human lifetime, assuming they have the technology and motivation. The Voyager Golden Records are another example. Launched in 1977, both Voyager probes carry gold-plated records containing sounds and images from Earth. They include greetings in 55 languages, music from different cultures, and even encoded images showing human anatomy and Earth's location in the galaxy. The intention was to create a message for any extraterrestrial intelligence that might find them, but the probes also reveal where we are. They're travelling slowly, so they won't reach another star system for tens of thousands of years, but if someone intercepts them, they have a map back to us. Irreversibility is the core of the horror. You can't take back what you've already transmitted. The damage is done. If the dark forest hypothesis is correct, we've already painted a target on ourselves. The only question is whether anyone noticed and how long it takes them to respond. Decades? Centuries? Millennia? The uncertainty means you live in perpetual anxiety. Every year that passes without incident makes you wonder if you're safe, or if the response is just slow. You never get resolution. Fear without a villain is more psychologically corrosive than fear with one. When you have an enemy, you can hate them. You can blame them. You can focus your fear into anger and action. You can build defenses, make plans, rally allies. But when the threat is structural, when it's just the way the universe works, there's nothing to fight. You can only accept the new rules and live under them. You can't punch the darkness. You can only hide from it. Let the silence linger. That's what a warning would do. It wouldn't elaborate. It wouldn't explain. It would just stop, leaving you to figure out what it means and whether you're going to listen. Because the warning only works if you change your behaviour. And changing your behaviour means accepting that everything you thought about humanity's place in the universe was wrong. We thought we were explorers, pioneers, the first to look up and wonder. But what if we're just the latest in a long line of civilizations that made the same mistake? What if the galaxy is full of ruins belonging to species that were too loud? What if silence isn't the absence of civilization, but the presence of civilizations wise enough to hide? And what if we're running out of time to join them? Part 12. AI and SETI. Shrinking detection. Windows. Technosignatures might have an expiration date. This is a recent realization among SETI researchers, and it changes the entire search strategy. If civilizations follow certain technological trajectories, they might only be detectable for a brief period. A few hundred years, maybe 1,000. After that, they transition to technologies that don't emit detectable signals. Think about Earth's radio emissions. We've been broadcasting for about a century, but those broadcasts are already declining in strength. Modern communication uses fibre optic cables instead of radio waves. Satellite transmissions are tightly beamed rather than omnidirectional. Digital compression makes signals more efficient, which means less wasted energy radiated into space. We're getting quieter not because we're trying to hide, but because quiet is more efficient. In another century, Earth might be significantly quieter than it is now, even as our civilization continues advancing. We'll still be here, still technological, still communicating. But our communication will be contained, point to point, encrypted. Someone looking at Earth from 100 light-years away might see a planet with oxygen in its atmosphere, but no radio signals. They'd have no way to know we're technological, unless they got close enough to see our cities, our satellites, our altered climate. AI-driven civilization transitions could accelerate this process. Once artificial intelligence surpasses human-level cognition, communication might shift to forms we can't intercept. Neural interfaces could replace electromagnetic transmission entirely. Data transfer could happen through quantum entanglement, which doesn't propagate through space in detectable ways. Computation could become so efficient that waste heat drops below ambient temperature variation. An AI civilization might be more advanced than ours, but completely invisible to current search methods. Short detection windows create a sampling problem. If techno-signatures only last a few centuries per civilization, and civilizations are spread across billions of years of galactic history, the odds of two civilizations being detectable at the same time are low. It's like trying to see two fireflies flash simultaneously in a vast field at night. They're both there, they're both flashing. But their light only lasts a moment, and the chances of both moments overlapping from your perspective are slim. We might be searching for signals that existed 1 million years ago, or won't exist for another 1 million years. Synchronization matters. The galaxy could be full of civilizations, but if they're all in different phases of technological development, we'd never detect each other. We'd be ships passing in the night, each one flashing its lights at times when no one else is looking. The idea of post-observable intelligence is unsettling. It suggests that the most advanced civilizations are the ones we can't see. Not because they're hiding necessarily, but because their technology is so refined it produces no detectable byproducts. They've transcended the messy, noisy phase of technological development. And from our perspective, they're indistinguishable from empty space. They could be everywhere. They could be watching us. We'd never know. This inverts our assumptions about the search. We've been assuming that advanced civilizations would be loud, that they'd build Dyson spheres and megastructures, that they'd terraform planets and light up the galaxy with their industry. But what if advancement means the opposite? What if maturity means minimalism? What if the most successful civilizations are the ones that learn to do more with less, to operate so efficiently that they leave no trace? Connecting silence to efficiency makes evolutionary sense. Natural selection applies to technologies too. Systems that waste energy lose out to systems that don't. Communication methods that reveal your position to potential threats lose out to methods that don't. Over time, civilizations converge on quiet efficiency. Not because they're afraid necessarily, but because it's optimal. Loudness is waste. Waste is disadvantage. Disadvantage leads to failure. Why loud civilizations might not last is a different question with darker implications. Maybe inefficient broadcasting correlates with other vulnerabilities. Maybe civilizations that haven't learned to minimize their signature also haven't learned to manage other existential risks. Climate instability, nuclear proliferation, engineered pandemics, unaligned artificial intelligence. Loudness might be a symptom of immaturity, and immature civilizations self-destruct before they learn restraint. Survivorship bias applies to the civilizations we might detect. If only young or reckless civilizations broadcast, then SETI is selecting for exactly the kinds of civilizations that don't last. We're searching for the doomed ones. The survivors are invisible, and if we do detect someone, it might mean they're about to disappear. They're in the window. The brief dangerous window between discovery of radio and discovery that radio was a mistake. Framing Earth as immature isn't about self-deprecation. It's about recognizing where we are in the developmental timeline. We're a single-planet species with primitive propulsion technology and no planetary defense against external threats. We can barely detect asteroids in our own solar system with enough warning to do anything about them. We have no way to defend against intentional attack from a more advanced civilization. We're vulnerable because we're new at this, and we're loud. We're broadcasting our presence without understanding the consequences. We're the teenagers of the galaxy, playing music too loud at a party, unaware that the neighbours have already called the police. Except the police might not be coming to shut down the party. They might be coming to eliminate the noise permanently. Reinforcing the danger of visibility connects back to the warning hypothesis. If advanced civilizations know that visibility correlates with extinction, they'd warn newcomers who don't know yet. Not out of altruism necessarily, but out of pragmatism. Fewer loud civilizations means fewer opportunities for predators to hunt. A quieter galaxy is safer for everyone who's learned to be quiet. Warning the loud ones benefits the quiet ones. It's enlightened self-interest. This ties directly back to the Dark Forest warning. If 3i Atlas carries any message, it might not be about the object itself. It might be about our behaviour, about the fact that we're still broadcasting without understanding the stakes, about the need to stop before something notices, before the window closes, not because we matured, but because we were eliminated. The message isn't, here we are, it's there you are, and that's dangerous. Part 13. Multi-messenger astronomy and what we miss. Multi-messenger astronomy is the practice of observing cosmic events using multiple types of signals: light, gravitational waves, neutrinos, cosmic rays. Each type of signal carries different information. Light tells you about chemistry and temperature. Gravitational waves tell you about massive objects accelerating violently. Neutrinos pass through matter and reveal nuclear processes happening inside stars. Cosmic rays are high-energy particles that might point back to their sources if you can trace their trajectories through galactic magnetic fields. The reason this matters is that single-channel observation is incomplete. If you only look at visible light, you miss X-rays and gamma rays. If you only monitor radio waves, you miss gravitational waves. Each type of signal reveals different aspects of the same phenomenon. A neutron star merger produces gravitational waves, gamma-ray bursts, and eventually a kilonover that shines in visible light. Miss any one of those channels and you miss part of what happened. The 2017 detection of GW 170817 was groundbreaking because it combined all these channels. LIGO detected the gravitational waves. Fermi and Integral detected gamma rays. Dozens of optical telescopes watched the afterglow. This single event confirmed that neutron star mergers create heavy elements like gold and platinum. It validated decades of theoretical models, but it only worked because we were watching with everything we had. Fast radio bursts are an example of how easily signals hide. FRBs are millisecond duration pulses of radio emission from cosmological distances. The first one was discovered in 2001, but it wasn't recognised as a new phenomenon until 2007, when someone was reviewing archived data. We weren't looking for them because we didn't know they existed. Now we know they're common, happening thousands of times per day across the observable universe. But we still don't understand what causes most of them. Some FRBs repeat, some don't. Some come from galaxies with active star formation. Some come from older, quieter galaxies. The diversity suggests multiple mechanisms, but we can't observe the sources directly. We only see the bursts themselves. It's like trying to understand an animal by studying the sounds it makes without ever seeing the animal. You get clues, but you're missing the full picture. Transient events are another category of things we miss. Supernovae last weeks, gamma-ray bursts last seconds. Tidal disruption events where a star gets torn apart by a black hole can last months, but the initial brightening happens in days. If your telescope is pointing at the wrong part of the sky when one occurs, you don't get a second chance. This is why networks of automated telescopes scan continuously, flagging anything that changes. But even with automation, coverage isn't complete. The Vera Rubin Observatory, when it comes online, will photograph the entire visible sky every few nights. That sounds comprehensive until you realise that events lasting hours or minutes will be missed between observations. You can't watch everything constantly. You have to choose. And every choice is a gamble that you're not missing something crucial. Misclassification risks are real. Algorithms flag anomalies based on how much they deviate from training data. But if the training data doesn't include examples of a particular phenomenon, the algorithm might categorize it as instrumental error. Early pulsars were almost dismissed as interference. Someone literally wrote LGM for little green men on the printout as a joke. If the signal had been slightly less regular, or if the researcher had been less persistent, we might have dismissed it as noise. Fast radio bursts were initially thought to be glitches. The first few detections were ignored because they seemed too unlikely. Only after multiple detections from independent telescopes did anyone take them seriously. The pattern only becomes clear when you accumulate enough examples to rule out random noise. But if you're dismissing examples as noise, you never accumulate enough to see the pattern. Unknown unknowns are the hardest problem. You can't search for something if you don't know it exists. You can't design instruments to detect signals you haven't imagined. Every discovery of a new type of astronomical object was preceded by stumbling across it accidentally while looking for something else. Pulsars were discovered while studying interplanetary scintillation. Cosmic microwave background radiation was discovered while testing a radio antenna for satellite communication. This means our understanding of the universe is biased toward the things our instruments happen to detect. We've built telescopes optimized for certain wavelengths, certain timescales, certain types of events. Anything outside those parameters is invisible to us, not because it doesn't exist, but because we're not looking for it in the right way. Observational blind spots exist in every survey. Satellites in low Earth orbit can't see through the planet. Ground-based telescopes can't see through clouds or atmosphere at certain wavelengths. Radio telescopes are drowned out by human-generated interference near cities. The galactic plane is so crowded with stars that finding individual objects is difficult. The Milky Way's dust obscures optical light from the galaxy's far side. We monitor a tiny fraction of the sky at any given time, and even that monitoring is constrained by available funding, telescope time, and human attention. Detection lag is another issue. From the moment a signal arrives to the moment someone realizes it's significant can take years. Data gets archived. Algorithms process it later. Patterns emerge only after multiple observations. The WOW signal from 1977 is still unexplained, partly because it was detected in archived data and was never observed again. By the time someone realized it was unusual, the moment had passed. We can't go back and look again. We can only speculate about what it was. Cosmic near misses are events we detected only because we got lucky. If timing had been slightly different, if our instruments hadn't been pointed in that direction, if the signal had been weaker, we'd have missed it entirely, and we don't know how many we've already missed. For every fast radio burst we've detected, how many occurred when no telescope was watching? For every gravitational wave event we caught, how many merged before LIGO was turned on? Framing ignorance as dangerous isn't about creating paranoia. It's about acknowledging limitations. We assume that if something important happens in the cosmos, we'll detect it. But that assumption is wrong. Most of what happens unobserved. And if an intelligence wanted to communicate without being obvious, they could easily exploit our blind spots. They could send signals in wavelengths we don't monitor. They could use timescales we're not watching. They could embed messages in natural-looking phenomena that we dismiss as astrophysical noise. This reinforces the caution necessary when interpreting objects like 3i Atlas. We're seeing one moment in its journey, captured by instruments designed to answer specific questions. Anything outside those parameters might be invisible to us. The message might already be there. We just don't have the right receiver. Part 14. AI Signal. Hunting and Misclassification Risk. Artificial intelligence has transformed how we search for anomalies in astronomical data. Machine learning algorithms can process terabytes of information faster than human astronomers can review it. They flag unusual patterns, categorize objects, and prioritize targets for follow-up observation. This has accelerated discovery rates across every field of astronomy. But it's also introduced new failure modes that could cause us to miss exactly what we're looking for. AI anomaly detection works by learning what normal looks like. You feed the algorithm training data containing examples of known phenomena, stars, galaxies, comets, asteroids, instrumental artifacts, cosmic rays, satellite trails. The AI builds a statistical model of normality. Then it scans new data and flags anything that deviates significantly from that model. The further something deviates, the higher its anomaly score. Simple in concept, complicated in practice. Bias in training data determines what the AI considers normal. If your training set contains mostly nearby, bright objects, the algorithm might flag distant, faint objects as anomalies even if they're common. If you trained it only on data from one telescope, it might misinterpret data from another telescope's instrument signature as unusual. If your training set includes very few examples of rare phenomena, the AI learns that those phenomena are noise rather than signal. Every AI inherits the assumptions and limitations of its training process. The Breakthrough Listen project uses machine learning to search for techno-signatures in radio telescope data. They've collected petabytes of observations from thousands of stars. Humans can't review that much data manually, so they train algorithms to identify narrowband signals that don't match known interference sources. The problem is that interference sources are diverse and constantly changing. New satellites launch, new electronics come online, radio regulations change. The algorithm has to distinguish between artificial signals from space and artificial signals from Earth. It's not always clear which is which. False positives versus false negatives is the fundamental trade-off. If you set the anomaly threshold too low, you flag everything unusual and drown in false alarms. Astronomers waste time investigating phenomena that turn out to be instrumental glitches or cataloguing errors. If you set the threshold too high, you miss real discoveries. The signal you're looking for might be just below your cutoff, dismissed as noise because it wasn't weird enough to trigger review. Most systems err on the side of false positives because missing something important is worse than wasting time on noise. But this means astronomers spend significant effort investigating phenomena that turn out to be mundane. After enough false alarms, you develop alarm fatigue. You start assuming that flagged candidates are probably nothing. You review them less carefully. And that's when you miss the real signal. It gets lumped in with everything else and dismissed without proper analysis. Automation trust is a psychological issue. When an AI flags something as significant, humans tend to believe it. The algorithm wouldn't flag it if it wasn't important, right? Except algorithms make mistakes. They have blind spots. They misclassify things. But there's a cognitive bias where we treat computer output as more reliable than human judgment. When an AI doesn't flag something, humans assume it's unimportant. But the AI is just following rules. It doesn't have intuition. It doesn't have context. It can't recognize something it wasn't trained to find. Over-relying on automation means you stop checking the things the AI ignored. You trust that if something was significant, it would have been flagged. But what if the signal is subtle? What if it's embedded in data that looks normal by every metric the AI was trained on? What if the intelligence sending it understood exactly how our detection systems work and crafted the message to slip through unnoticed? You'd never find it. Not because you weren't looking, but because your AI was trained to ignore it. Human oversight limits are about cognitive bandwidth. A human can carefully review maybe a few hundred candidates per day. An AI can process millions. This speed advantage is essential for modern astronomy, but it creates a bottleneck at the verification stage. Most flagged candidates never get human review unless they meet additional criteria. This means the AI's initial judgment filters out most of the data before humans see it. You're trusting the AI to make the first cut, and first cuts are where things get lost. Feedback loops develop over time. When an AI flags something and humans confirm it's real, that information goes back into the training data. The AI gets better at finding similar things, but it also gets narrower. It learns to find what humans confirm, which means it reinforces existing biases. If humans keep confirming one type of anomaly, the AI learns to prioritize that type, and might start ignoring others. The system optimizes for past successes, which makes it worse at finding future surprises. Misinterpretation consequences in astronomy are usually academic. If you misclassify a galaxy as a star, you publish a correction and move on. Careers aren't ruined over misidentifications, but misinterpretation of potential technosignatures has different stakes. If you dismiss a real signal as instrumental noise, you miss first contact. Humanity's biggest question remains unanswered because an algorithm made a categorization error. If you misidentify natural phenomena as artificial, you cause false alarm, institutional embarrassment, and credibility damage that makes future claims harder to believe. The 1967 pulsar discovery almost didn't happen because the signal looked too artificial. It was so regular that researchers initially thought it was human-made interference. They labelled it LGM-1 as a joke, little green men. Only after finding more pulsars with similar properties did they realise it was natural. But imagine if they'd stopped there. If they'd dismissed it as interference and moved on, we'd have missed pulsars entirely until someone else stumbled across them years later. Connecting to message misreading is where this gets existential. If an intelligence sends a warning and we misinterpret it as natural phenomena, we miss the warning. We continue the behaviour that prompted the warning. We stay loud, we stay visible, we stay vulnerable. If they send a signal designed to be ambiguous and our AI categorises it as noise we never investigate, the message gets lost not because we weren't listening, but because we didn't recognise what we were hearing. Framing AI as amplifier, not oracle, is the responsible position. Artificial intelligence makes us better at finding patterns. It extends our capabilities. It processes data at scales impossible for humans. But it doesn't make us infallible. It doesn't replace judgment. And when the stakes involve existential questions about our place in the cosmos, about whether we're being watched or warned or hunted, relying too heavily on automation is a gamble we might not win. The irony is that we're using artificial intelligence to search for artificial intelligence. We're trusting algorithms to recognise minds that might think nothing like algorithms. We're assuming that whatever's out there will announce itself in ways our systems are designed to detect. But what if they don't? What if the message is already in our data, filed under noise, waiting for someone to look at it the right way? Part 15. Broader cosmic threats and final reflection. Recent planetary defence successes give us a false sense of security. NASA successfully diverted the asteroid Dimorphos in September 2022 using the DART mission. Double Asteroid Redirection Test. A spacecraft deliberately crashed into a small asteroid moon to change its orbit. The mission worked. The impact altered Dimorphos's orbital period by over 30 minutes. Proof of concept. We can, in principle, protect ourselves from asteroid impacts, but that capability is limited. We need years of advance notice. The asteroid needs to be small enough that kinetic impactors work without fragmenting it into multiple dangerous pieces. It needs to be on a predictable trajectory that we've calculated precisely. It can't be a comet, because comets behave unpredictably as they outgaze. It can't be coming too fast, because then we don't have time to launch an interceptor. Most cosmic threats don't meet those criteria. Contrasting known threats versus unknown ones clarifies the problem. Asteroids are known threats. We've catalogued most of the large ones. We're working on the smaller ones. We have models for impact frequency and potential. Damage. We know roughly how much warning we'd get based on size and detection capabilities. Unknown threats are everything else. Rogue planets ejected from other stellar systems travelling through interstellar space. Comets from the Oort cloud on long-period orbits we haven't mapped yet. Gamma-ray bursts from collapsing stars light years away. Solar flares powerful enough to strip our atmosphere. Phenomena we haven't imagined yet because they exist outside our current physics. You can't prepare for what you don't know exists. This is the fundamental challenge of existential risk mitigation. You can build defences against specific threats, but general resilience is harder. How do you protect against something you can't predict? The best answer is redundancy. Multiple planets, multiple habitats, distributed backups of civilization. But we're nowhere near that level of capability. We're still a single-planet species with all our eggs in one fragile basket. Biosignature ambiguity is a related issue in the search for life beyond Earth. When we detect oxygen in an exoplanet's atmosphere, we interpret it as potential evidence of life, because on Earth, oxygen is produced by photosynthesis. But oxygen can be produced by non-biological processes. Photodissociation of water vapour by ultraviolet light creates oxygen without biology. Volcanic outgassing can release oxygen if the chemistry is right. Distinguishing life from mimics requires more data than we currently have for most exoplanets. This means biosignatures are hints, not proof. Suggestive, but not conclusive. And if we can misread biosignatures, we can misread technosignatures too. A signal that looks artificial might be natural. A pattern that looks like communication might be noise. Or worse, a phenomenon that looks natural might be artificial. The universe doesn't label things for our convenience. We have to figure it out ourselves, knowing that we might be wrong. Reflecting on the Fermi paradox again brings us full circle. Where is everyone? We've spent 15,000 words exploring possible answers. Maybe they're hiding. Maybe they've gone quiet. Maybe they've transcended physical form into something we can't detect. Maybe they existed long ago and left no traces. Maybe they're coming but haven't arrived yet. Maybe they're here but we don't recognize them. Or maybe the Great Filter is ahead of us, not behind us, and most civilizations don't survive long enough to become spacefaring. The Great Filter hypothesis suggests that at least one step in the evolution from non-life to spacefaring civilization is extraordinarily improbable. If the filter is behind us, in our past, then we're lucky to be here, but the galaxy might be full of life once it gets started. If the filter is ahead of us, in our future, then we're approaching something that kills most civilizations: nuclear war, climate collapse, unaligned AI, nanotechnology accidents, or something we haven't thought of. Something that waits for every civilization at roughly the same technological level we're reaching now. Survival versus curiosity is the tension at the heart of this entire discussion. Curiosity drives exploration. It makes us search for answers, broadcast our presence, reach beyond our planet, build telescopes and transmitters and spacecraft. Curiosity is what makes us human. But survival might require restraint. It might require accepting that some questions are too dangerous to ask loudly, that some discoveries come with existential risks, that the universe might be less welcoming than we hoped. This isn't an argument against exploration. It's an argument for caution, for thinking through consequences before we commit to irreversible actions. We've been broadcasting for a century already, that's done. But we can choose what we do next. We can choose whether to amplify our presence or minimize it, whether to shout or whisper, whether to assume we're safe or assume we're not. Reframing silence as adaptation suggests that the great silence isn't emptiness. It's populated by civilizations that learn to survive by learning to hide. They're out there, watching, listening, existing quietly in the spaces between the noise, and the reason they're not talking is that talking is how you die. They've learned something we're only beginning to consider, that in a universe where predators might exist, prey stays quiet. The final question is simple and terrible. What if survival means restraint? What if the cost of continuing to exist as a technological civilization is giving up the very thing that makes us explorers? Our curiosity, our drive to reach out, our need to answer the question, are we alone? What if the answer is yes, but only because everyone else learned to shut up, and you need to do the same? 3i Atlas reaches its closest approach on December 19th. By then we'll have more data, more observations, more analysis. Debates will continue, papers will be published, the internet will speculate. And maybe, if we're very lucky or very unlucky, we'll have an answer to the question we didn't know we needed to ask. Not, are we alone? But, should we stay quiet? The scariest message isn't the one that declares war. It's the one that tells us we've already lost by announcing we exist. That the game was over the moment we made noise. That the universe isn't empty. It's just learned to whisper. And we're still shouting into the dark, hoping something answers, not realizing that silence might be the only thing keeping us alive. On December 19th, maybe nothing will happen. 3i Atlas will pass. It'll continue its journey out of the solar system. Years from now, it'll be a footnote in astronomical catalogues. Another interstellar visitor that came and went. Another mystery we couldn't fully solve. Or maybe we'll notice something. A pattern we missed before. A correlation that shouldn't exist. A message hidden in data we thought was noise, and we'll have to decide what to do with that information. Whether to respond, whether to change our behaviour, whether to accept that the rules we thought governed the universe are wrong, and the real rules are far more dangerous than we imagined. Either way, December 19th marks something. A date when we were forced to consider possibilities we'd rather ignore. A moment when comfortable assumptions about our place in the cosmos became uncomfortable questions. A time when we had to ask ourselves, if we received the scariest message possible, would we even recognize it? And if we did recognize it, would we be brave enough to listen?